Hi, I'm Zach Lifton, hazards geologist at the Idaho Geological Survey. This video is a virtual field trip to the site of the 1983 Borah Peak earthquake. Borah Peak is just over my right shoulder here, and it's the highest point in Idaho at 12,662 feet. It's no coincidence that there is significant seismic activity associated with the tallest mountain range in the state. Charles Darwin recognized that earthquakes were related to mountain uplift. In 1835, Darwin was visiting Chile when the magnitude 8 Concepcion earthquake struck. He experienced the shaking and witnessed the evidence left behind, particularly the uplifted shorelines. Darwin realized that earthquakes build mountains, and we are seeing the same process here in the Basin and Range. In this video, I want to show you some evidence of an earthquake, the largest that we've recorded in Idaho's history, and talk a little bit about earthquake hazards in Idaho. The earthquake left behind a really well-preserved and easily accessible fault scarp, which you can see as a sharp white line at the base of the slope behind me. You can visit this earthquake scarp where it crosses Double Springs Road, Rock Creek Road, Birch Springs Road, or Arentson Gulch Road, which are all accessible from Highway 93 north of Mackey. These mountains are here because tectonic forces have been stretching out the Earth's crust, breaking it along faults, and causing large blocks to tilt up. The tilted blocks make up the mountain ranges, and the gaps in between get filled in with sediment and become the valley floor. This pattern of geologic expression is called the Basin and Range province. The magnitude 6.9 Borah Peak earthquake occurred on this section of the Lost River Fault on October 28, 1983. It was the largest earthquake recorded in modern times in Idaho. It caused about $12 million in damage and killed 2 small children in the town of Chalice when bricks from a building facade fell. The Borah Peak earthquake created a 34-kilometer long ground rupture called a fault scarp. At its maximum, the fault scarp from this earthquake is 2.7 meters high. In addition to the fault scarp, the earthquake also produced some really dramatic groundwater effects down in the valley, including sand boils and artesian springs, which changed well levels across the entire region. Fault scarp is the surface expression of a fault rupturing the ground surface. And here it's expressed as a steep slope between 2 flatter surfaces. I'm standing on the lower surface. The upper surface is also about the same slope here. And when the scarp forms, it's typically nearly vertical, or it can be. Here you see that it's actually laid back a little bit. It's been, some of the material, some of this gravel here has started to work its way down and smooth out a little bit. But this is actually still a really good example of a relatively young fault scarp. This is less than 40 years old, and it's really easy to see out here. It's really light colored because the gravel and cobbles and sand and silt are exposed. There's not much vegetation on it, and that makes it really easy to see it in air photos or satellite photos, or just as you're driving down the highway. Earthquakes actually form by movement of the crust along a fault. And so there's several different kinds of faults that create earthquakes. This fault and many of the others in the Basin and Range are normal faults. And so let's take a look here real quick at what that means. So there's 3 kinds of faults that we typically categorize most faults as: normal, reverse, and strike slip. So in cross-section, a normal fault will look something like this, where one side moves down relative to the other, and this side is called the hanging wall. I'll just abbreviate it as HW, and you can remember that because it looks like it's overhanging. And this side is the footwall, and you can remember that by thinking about if there's a little tunnel dug along the fault, your feet would be on the footwall, and the hanging wall or head wall would be above you. Okay, so a reverse fault has similar geometry, but the sense of motion is opposite. So in this case, the hanging wall actually moves up. So that's opposite from a footwall, from a normal fault where the hanging wall goes down. And a strike slip is a bit different. These are both cross-section views. If we looked at a strike slip fault in map view from straight down, you'd see the crust moving past each other along the fault side by side. There's no vertical motion. However, in nature, it's not always this clean. So sometimes you'll have a combination of some of these faults. And around the world, you can find these faults everywhere, but a very typical strike slip fault example would be the San Andreas. The Borah Peak Lost River fault here is a great example of a normal fault. And an example of a reverse fault at a really big scale would be something like the subduction zone in Cascadia. The Lost River Range is located in a pretty remote part of Idaho, which makes it all the more amazing that 4 eyewitnesses saw this fault scarp rupture the ground surface. 2 of those eyewitnesses were a husband and wife hunting for elk early in the morning here in Arentson Gulch. Just after 8 a.m., they heard the earthquake coming from the south before they felt it. Then as the shaking started to build, the husband actually felt motion sick to the point he had to sit down. And just as the 30 seconds or so of the strongest ground shaking was subsiding, they saw practically in front of them this fault scarp rupture across the landscape like a zipper from the northwest to the southeast. And it formed this 1.5 meter tall scarp that we see here today, preserved pretty well in the landscape. Geologists study ancient earthquakes to try to understand the timing and size of past events and tell us a little bit about what we might expect in the future on a fault. This field of study is called paleoseismology, and it's done by digging deep trenches across the fault and looking at the stratigraphy or the layers of sediment within those trench walls. Last year, at the base of the mountains there, a team of geologists excavated a paleoseismic trench and collected data to try to understand what happened on this fault before 1983. The 1983 rupture didn't actually cross this part of the mountain front, but we know that there were earthquakes there in the past because there is an older scarp. And so they're collecting information to figure out how big earthquakes are, how many have occurred, and when they occurred. So when you're looking inside a paleoseismic trench, what you want to look for is some evidence that an earthquake occurred, formed a fault scarp, and then it got buried, and then another earthquake occurred. So in cross-section, one of the walls of the trench might look like this. You've got a relatively flat surface on top, you got the scarp, and then a relatively flat surface below. And since we're looking at this in cross-section, we can see all the layers of sediment in there. So perhaps we have something like this out here. But at the scarp, we know there's a fault that formed that scarp, so we can assume a fault line in there, and you can see that in there because all the sediments are offset. But more importantly, after this scarp is formed, some of that material erodes down and fills in on the lower surface. So it starts to look like this. And you end up with a little triangular package of sediment that's called a colluvial wedge. And in this case, this colluvial wedge is basically at the surface, but when you dig down, you can often find these colluvial wedges buried. And that's indication that there was an older earthquake on this fault occurring in the same place. In this case, we know there were 2 earthquakes, and geologists have several techniques for actually getting an age for when or for how old these sediments are. And one of those is through carbon dating, radiocarbon. In a landscape like this, every so often there's a wildfire, and that wildfire leaves behind charcoal. And charcoal breaks down, gets mixed in with the soil, and gets preserved in these colluvial wedges. And so if you can find some charcoal, even microscopic sized pieces, those can be dated pretty precisely, and it gives you a pretty good idea of when that colluvial wedge formed and therefore when that earthquake might have occurred. Another technique for dating these sediments is called optically stimulated luminescence, and sometimes it's just abbreviated as OSL. And this technique uses sand-sized sediments usually, and those sediments are collected in the dark so that they're not exposed to sunlight, because the theory here is that they're buried and they're no longer exposed to light once they're buried. And that starts a sort of a clock inside of the crystal grains. And if we remove those and keep them in the dark, take them to a lab and expose them to a special kind of light, they give off a certain signal that we can measure, and it's proportional to how long it's been buried. So the longer it's been buried, the more signal it gives off. So OSL is another way to figure out how long that colluvial wedge has been buried, and therefore when that earthquake occurred. This is the fault scarp created by a magnitude 6.9 earthquake. That's the largest recorded event in modern history in Idaho. The second largest event was a magnitude 6.5, which happened just about 80 kilometers from here in Stanley, Idaho. That earthquake was large enough to cause some damage, but it didn't leave any trace on the surface, no fault scarp, no evidence that we could look at years or decades or millennia from now. And since we typically base our seismic hazard on where earthquakes have happened in the past, it means that there's a possibility that earthquakes can occur where we don't expect them. Our understanding of seismic hazards relies on finding evidence for past earthquakes. In this virtual field trip, we showed you a lot of clear evidence for the Borah Peak earthquake. We can't predict earthquakes, but we can still learn a lot more about them. And the best advice is to just understand that you're in earthquake country and be prepared for the next event. Thanks for joining this virtual field trip.